Hello again, pre-calculus. Welcome back to pre-calculus. It's good to be talking with you again and to get through this lesson. Um, Man, if someone hasn't told you yet, make sure you know, especially today. Uh, I want you to know every day, like that you are deeply and incredibly loved by the staff, particularly by me. Um, I love teaching you all, and I miss seeing your face, but it's I love working with you. That said, also know that we, the both of us, we are loved incredibly by a holy God. Um, I need to be reminded that sometimes. Um, so I know that a lot of us have, well, I particularly have trouble with schedules and making sure that I have everything scheduled out in the right time and that I don't, and I like keep things to a particular rigor. And I've been wanting to do this since we started during class, and I haven't gotten a chance to start it. But I think this would be a good time to start it here. I'm a big fan of what's called the Pomodoro technique, or at least I'm a decent fan enough of it. I think it's pretty reasonable. The idea is that in order to be the most efficient at all of your work, you actually need to take breaks. And so the question is, how do you take ideal breaks so that you are the absolute most efficient at work and get the most done in the least amount of time? Well, one guy started discovering in his own personal experience, it seems to be like a 30-minute, 5-minute toss back. You do 30 minutes like really hard crunch work, then you take a 5-minute break. And then you do another 30 minutes of hard work, then a 5-minute break. You do that 4 times, and you take about a longer break. I think it's about 45 minutes upwards. Depends on who you're talking to. Sometimes it's at 20, sometimes it's 45. Anyway, I wanted to try that here in this video. So I'm going to try to start this sand timer that I have. That's roughly 30 minutes. So it's supposed to be 30 minutes, give or take a few seconds. And and once that runs out, we're going to take a 5-minute break. If this ends up being a 30 minutes, and for every 30 minutes we'll take another 5-minute break. I just wanted to try to keep us on track so we don't get overwhelmed with all this. But that said, you can be fully engaged for this next 30 minutes as we really hunker down. Before we start though, I wanted to make sure that you at least remember your unit circle. If you have your unit circle, make sure you have it in your head because you'll need it for this lesson. If you don't have it, make sure to get one, print it out, or have them with you because that's going to become very useful. I'll wait for you to get yours before we start. Okay, assuming you have it, let's go ahead and start the timer and kind of try this new thing that I'm working on. All right, you have to keep me on track because I may forget that that's there. Good luck on keeping me on track though. We'll see what we can do. All right, so this lesson's at polar coordinates. It's you remember those different functions in the calculator? How you had like func and par and all of that different stuff. Yeah, we had func and par. Now we're gonna learn the third function called polar. And here's the idea. I think that polar coordinates came out of mathematicians wanting to save energy and not work as hard. They're like, this is writing a lot of these coordinates on the graph is just it can be daunting. And so they said, well, let's find an easier way to write coordinates that doesn't take as long. And it ended up being a whole system of doing things and a whole framework of understanding the world. But if you can do it, then it might actually save you a decent amount of time when you do work because you can just instead of trying to write this really fancy thing, I'll try the polar coordinate. Here's what I mean. I'll try to explain it with an example. Um, so think about this. Where I'm standing right now, DC, the District of Columbia, is about that direction. Right in that direction, about 25 miles, and well, actually more about that direction. Yeah, actually kind of right behind me. If I go this direction about 25 miles, I'll get to DC, and let's see, east is right about there. So if I was to kind of plot myself on a coordinate graph, if I want to figure out how to get to DC, here's what I'd say. I would say, from 0 degrees on a normal graph, which is kind of like east for most of us, well, for all of us, if I start from pointing east, if I rotate to about 60 degrees and then head 25 miles, I will get to the District of Columbia. I'll get to DC. And and so I could say, and I could ask like, where is DC? How do I get to DC? I could say, I could say I'm starting from here. This is home, and and I could say I'm gonna go all the way up here, and I gotta figure out where this coordinate is. I would say go to that coordinate. You know, and we do that. We have coordinates for the graph. We have latitude and longitude. We have it all graphed out. We can do that, and I could figure out what that coordinate is by saying, okay, this is 60 degrees, and this is 25 miles, and then I could write down. I could figure out what the how far I go to the right and get the x coordinate, and how far to the left and get the y coordinate. And I could say, okay, you go to this x, y coordinate, and you could do that, and you could, you know, use the Pythagorean theorem and figure this out, and because this is a right triangle and all of that, and that's well and good. But that takes a long time, you know. It takes a good decent chunk of time. It seems like why can't we just say, instead of having to pull a Pythagorean theorem every time we want to get directions to somewhere, why can't we just say, I want to go 25 miles in the direction of 60 degrees. And mathematicians were like, we should be able to do that. And they said, let's do it. So they said, we'll call this a polar coordinate. And they said, okay, every single time when we want to write a polar coordinate, and it's unfortunate the way they made it. I think they should have made it a better way, so it doesn't just use parentheses and looks exactly the same as a rectangular coordinate. And before, yeah, but it looks in the exact same. It does look in the exact same way, but it is pretty straightforward. You say, I'm going 25 units, and I'm going to go that in 60 degrees. Or if you want to kind of think of backwards, I could say I'm pointing 60 degrees and I'm going to go 25 units in that direction, or 25 miles in that direction. That's kind of what we're saying here. That's really all a polar coordinate is. That's really the essence of what we're doing in this entire lesson, and trying to understand how to think about points. Not really in a sense of like it's this XY coordinate, but it's a certain distance and a certain number of degrees away from a certain point, a certain direction and a certain length. It sounds a little bit like vectors, doesn't it? It's a lot like vectors. It's almost like the language. In some ways, you can say it's kind of like the language of vectors. Fortunately, we're not in a stage yet where we're going to have to worry about vectors again. We're kind of going to set that aside and kind of work on this for a while. Okay. So we can look at this. We can read it. We can write it a couple of different ways. I could say, this is this point right here. That's 25. That's 25 and 60 degrees. I could say that in a bunch of different ways. Here's some ways I could say that. I could say, I just turn 60 degrees away from east, go 25 miles. But, you know, if you wanted to say something else, even if you want to be like, you know, fancy or whatever, you could say, okay, turn 60 degrees, then turn another 360 degrees, whole way around, and then go 25 miles, right? We could do that as well if you were so inclined. And so we could say, this is also equals, I could also say, instead of just saying 25, 60, I could say 25 and then 60 degrees plus 360 degrees. I could do that too. Or I could say, if I wanted to, you know, confuse people, or if I wanted to give someone a headache from spinning so much, I could say, okay, go start from east, turn 60 degrees, turn 360 degrees 3 times. I think it's 3. That's my 4 times. I don't even know anymore. And then go, then go in the direction. And so I could say 25, and then 60 degrees plus. I could say 4 times 360 degrees. 4 times 360 degrees. And that's the exact same thing as saying just go 25 and 60 degrees. I'll get to the same point. Because I can go 60 degrees, I can go 60 plus 360, 60 plus 360, or I could go 60 plus 360 plus 360 plus 360 plus 360. So that'd be 60 plus 360 degrees times 4. And so I could do that. Or 4 times 360 degrees. And so both those work. They're both just fine. And in fact, I could say any number I wanted to. I could say 25 and then 60 degrees plus n times 360 degrees. And I can say I can turn around as many times as I want and I'll still get to the same point. And so this is really interesting. It distinguishes itself a lot from the normal XY coordinates that you're used to. Because with the XY coordinates, we can only just say it one way. You got to go, I guess in this case, it'd be square root 25 over 2 and across, and then square root 25, no, 25 over square root 2, 25 over root 2 across, 25 over root 2 up, and that'll get to the point. So you kind of, those are the XY coordinates you got to go. This is, and there's only one way to write that. There's I guess you could say an infinite number of ways to write it, because you could just add 360 degrees over and over and over again as many times as you want. Or you could add negative 360 degrees. You could say 25 and then 60 degrees plus negative 2 times 360 degrees. That was when you go backwards. Yeah, I rotate backwards around 2 times. And that works as well. Oops. Okay, it's all right. And so there's multiple ways to write this. So you want to remember that for any coordinate, any polar coordinate, we can write it a couple different ways. We can say the first distance is the radius, and so here's the kind of official definition of a polar, or official formula to write all the polar coordinates. You can say it's the radius, and then you say it's the angle, the normal angle you're used to, and then we'll say plus n, any number, times 360 degrees. Or, as you'll see most times in the lesson, they like to use radians instead of degrees. So you'll often see, more commonly, you will see n times 2 pi. Or even more so, maybe even more accurately, they'll say 2 pi n. 2 n pi, 2 n pi. Because the constant, the coefficient usually goes first. That number usually goes first. They say 2 n pi is what they will say. But that's where it comes from. It's saying how many times I rotate around. Now, you think about there's that way to write it, but there's also another way I can think of getting the DC from here. Think about, let's say I said, I'm going to rotate 60 degrees, right? And then I say, how about this? Let's say I rotate another 180 degrees, right? So I'm facing the opposite of where I want to go. And then I'll walk backwards 25 miles. I'll go negative 25 miles. That's also a legitimate option. So I could say, let's use a different color for this one. Let's say I go 60 degrees, or I go 60 degrees and then I subtract 180 degrees, or maybe even add 180 degrees. That works as well. Let's say I'll go another 180 degrees. So 60 degrees and then 180 degrees. And then instead of going forward 180 degrees, I'm actually going to go backwards. I'm going to go backwards 25. So I'm going to go a negative 25 miles from where I'm facing. And now it'll get me to the exact same point. So instead of, again, I'm going negative 25 miles because I'm not going forward anymore. I'm going backwards 25 miles. That's kind of how that's working. So I could write this as if I wanted to, I could write this as negative 25, and then I could write it as, let's see, that'd be 60 degrees plus 180 degrees. Cool. And so I could say that, and then on top of that, I could even say, well, we could use the same rule we did before. I could say, if I spun around again, that would work as well. So I could say 180 degrees plus 360 degrees, maybe plus 2 times 360 degrees, 3 times 60 degrees, however many times I want. So I could say this is 180, and then on top of that, I could say, because this works, on top of that, I could say plus n times 360 degrees. So that's the full way to write that. Okay, so let's look at that then. So let's see, that would be, in this case, this is still the radius. I know, it's fine, it's okay if I'm offline. This is the radius, just like before. This is our theta. And let's see, we have 180 degrees, and then this is basically 180 degrees is pi, and then 360 degrees, that's 2 pi. So a way to make this a normal equation, another way to write the same thing again, is the radius, and then theta, and then plus pi, and then on top of that, we're going to add plus 2n pi. So that's a lot that's going on there. And there's a lot that's going on here, but we can still kind of make this work even with that. Or if you really want to get fancy, and you could factor something out and say pi times 1 plus 2n, but that's, you don't have to worry about that. So these are two formulas to find any number of ways to write the exact same thing. So in essence, you can pick any number. You can pick an infinite number of numbers and get to the same point. So whereas the normal thing, the xy coordinate is only one way. This is an infinite number of ways to write. There's an infinite number of ways to write a single polar coordinate. An infinite. And so I want to make sure you really get that down. There's an infinite number of ways to write these coordinates. Cool. So those are the two ways to write it. I mentioned two things so far. I mentioned the idea of rectangular coordinates, and I hope I haven't confused you by just tossing that word in there. A rectangular is exactly what we've been using this whole time. And you can remember it's a rectangular because we have the normal coordinate system, and we go, let's say, x number out and then x number up. So we go x across x up y. It's kind of like we make a rectangle. So we don't go across at all. We just go rectangularly, left and right and up. And so that is just, we have an x and a y coordinate. That's what the rectangular coordinates mean, because you kind of make a rectangle, or at least half a rectangle. So that's what's going on there. All right. So polar coordinates, rectangular coordinates, that's what's going on. That's what those are. Let's see how to, well, we've kind of looked at a little bit of how to graph a polar coordinate, but if it's still confusing, let's look at an example. So here's an example of a rectangular coordinate. This is what the rectangular coordinate system actually looks like. Instead of, we're used to this grid. It's a rectangular. This is what a rectangular system looks like. We're used to looking like this with boxes, and you kind of go a certain number of boxes right, a certain number of boxes up. But with a polar coordinate system, all we care about is how far we're going and in what direction we're going. So some students kind of like to think, for some students it's more helpful to first think about what direction and then how far. Say I'm first going 60 degrees, I'm first turning 60 degrees and I'm moving 25 miles. For some students, it's easier to think that way than to think I'm going 25 miles in 60 degrees. Whichever way is more helpful for you, then that's the way to do it. Okay, but we can see, if I want to say on the left hand side, I've got a radius that says, let's say I wanted to plot. Let's say I want to plot 25 miles. Let's say I want to go 25 miles. I can set my radius. The radius 25. There we go. 24. That's close enough. That's actually might be even more accurate. And then I'm going to go 60 degrees. If I go 60 degrees, my A will represent the number of degrees I have. 60 degrees. Whoop. And so I want to go about 60. And there we go. And that plots the point. So if I wanted to plot less space, I'd go closer. And if I wanted to, I'd have a smaller number for radius. And if I were to go have more space, I'd plot a larger number. Okay. And you can see that so that's one way to plot it. I could add I could add 180 degrees. So 60 degrees plus 180 would be 240. Or yeah, 240. 240. And so that's in the opposite direction. But if I went negative 24 now, so if my radius is about negative 24, negative 25, and I went 240 degrees, it still lands me in the same place because I'm going backwards now. That's kind of what's going on here. And of course, let's go back to the normal way. And if I add, I had 60 degrees before. If I add 360 degrees, that brings me to 420. 420. And that gets me in the same place again. That again puts me in the same place. So no matter how I planned it, I get the same thing. I always get the same number. I get the same spot. And that's kind of what we're trying to think of when we think of plotting this. You'll notice I use a special formula here. This is, for the x-coordinate, I use r cosine theta, and for the y-coordinate, I use r sine theta. The thing is, with Desmos, it doesn't actually let you can't just say, I want to go radius, and I want to go a certain radius and number of degrees. You have to actually put in a formula so that it does what you want. And I said, okay, you can only put in rectangular coordinates, so I had to convert it. So I said, for the rectangular coordinate x, I will put in r cosine theta, or in this case, r cosine a, which is our theta. And for the y-coordinate, I'll put r times the sine of theta, or r times the sine of a. You might remember why I do this. If you're thinking very closely, you might remember that this is the same thing as the parametric equations. So let's look at this. You'll remember that this, making x r cosine theta and y r sine theta, that's the same thing we do for parametric equation. These are the exact same things because it does the exact same thing. We take the radius of however far we want it to go, and we multiply that by the x coordinate. or where it would be on the x side. And we take that to find that where it would be. If we want to figure out what direction we'd put it, or where we'd put it in terms of x, we multiply it by the cosine of theta. If we want to figure out where to put it in terms of y, how to figure the y distance of theta, how far up that is, we would find the sine of theta, and then we'd multiply that by the radius, and that gets us our exact point. So this parametric equation is the exact same thing we'd use to find both a point and a whole equation, and in our case, a polar coordinate. These are the same things. So you don't have to learn anything new there, which is great. Now let's say we wanted to actually convert. We want to do a more rigorous conversion from one to the next. We want to say, let's say I wanted to figure out the exact coordinates of, oh, that's awful, excuse me. I want to figure out the exact coordinates of DC, where it is relative to my home. So I would put in 60 degrees, and I would say, 60 degrees. And let's say I would put in, 25. Yeah, we'd say this is 25, and we'd remember that this x, we have x and y. I want to figure out what x and y are. So we'd say x squared plus y squared equals 25 squared. That's kind of how we remember how to do these things, right? And that's exactly a part of our formulas. So if I want to figure out x and y, if I want to convert from polar to what's called rectangular, we could also have this tool of x squared plus y squared equals the radius squared. That's another tool we can use to kind of convert from one to the next. Okay, and finally, so that's the Pythagorean theorem, which is something you're used to. And finally, the other thing you might be used to is, the only thing you might be not be used to is how tangent of theta is y over x. There's two ways you can think of that. If you can think of that as if you've got the coordinates x and y, and you got 25, and you've got an angle, you could say tangent literally is y over x. You could think of it, so tangent theta literally is y over x. That's how you find tangent, opposite over adjacent. You could also think of it as we could divide this top equation. We could divide y equals r sine theta. We could divide that by x equals, r cosine theta. Because you can divide, remember from algebra, you can add equations, subtract equations. You can have multiply and divide equations in the same way. So y over x equals, the r's cancel out, sine over cosine is tangent of theta. So, okay. And that's really all the things we need. That's all the tools we need to do these lessons. From here on out, all we have to do is just remember these tools, and we should be able to figure out these problems. This is all you need to know. But that said, it's good for us to jump in and make sure that we are that we are doing these problems correctly. So if you want to, the rest of this is just gonna be me working through problems. If you want to work through the problems with me, great. I'm still watching the timer. If you don't want to do that and you just kind of like want to work on your own, then go ahead and go free and try your own, and then come to these problems as you need them. But here we go. I'm going to start with the first problem and see what we can do. Let's see. The polar coordinates of a point are given. Find its rectangular coordinates. Okay, so we want to convert from polar coordinates to rectangular coordinates. And let's see. If we're trying to think of the polar coordinates, the way that the Desmos kind of set it up, or the way that's always set up for polar coordinates, is it's kind of got, it's set up in such a way so you can kind of see different concentric circles, and each circle is kind of the radius. So you've got degrees. Degrees is one way of thinking about it. So you've got lines for degrees, and you've got lines for radius. That's kind of how this is set up. So when we think of this, it thinks we're trying to figure out the degrees and the radius, how far out it is, and we're trying to figure out how many degrees it is. That's what we're trying to do here. Okay, so let's see, we've got 6, 3 pi over 4. I'm going to write this a little bit bigger so it's kind of easier for us to see. So let's see, 6 and 3 pi over 4. So that's the polar coordinate. Okay, so what is that saying? That's saying I'm saying this is a length of 6. It's got a length of 6, and it's got a direction of 3 pi over 4. 3 pi over 4. You know, I think on the top, I'll just kind of, I'll put this in there afterwards. But this is r, we write the equation, we write the points in terms of r, then theta, if that was any kind of confusion to you. That's the kind of foundation we work with. Okay, so 6 and 3 pi over 4. We got to figure out what that coordinate is. Well, we can do a couple things to figure this out. We could figure out that this is 3 pi over 4, and 180 degrees, the full supplement, or complementary angle, yeah, is pi over 4. So that's pi over 4. We can just finish a triangle over here and work that out. So that's pi over 4. Then we've got at the bottom, let's see, this is our x coordinate and this is our y coordinate on top. And let's see, we want to figure out what that is. We can just use normal trigonometry. We can remember, or we can just remember these formulas here. X equals r times the cosine of theta, and y equals r times the sine of theta. Two ways of going about it. I'll try to do both real quick. So if we want to just use the normal Pythagorean theorem, we could say that 6 squared equals, well, actually we can't do the Pythagorean theorem yet, but we can remember that if I want to figure out its x, I'll just use my trigonometric properties. That is, let's see, that'd be adjacent hypotenuse, that'd be cosine. So cosine of pi over 4 is that would be, let's see, yeah, that'd be 6 over x. Or if you really wanted to, I think it'll still work if you just said, if you use the first angle, 3 pi over 4. You could say, you could even forget this first angle here and just use cosine of 3 pi over 4, and that'll work as well. If you remember, well, if you kind of ran into that problem when you're doing problems before, back a while ago with trigonometry. So cosine of 3 pi over 4 equals x over 6 over x. If I wanted to solve it from here, I could just solve it. Let's see. No, is it just no? I'm sorry. This is wrong. This is x over 6. I wrote that incorrectly. Excuse me. So this would be 6 times the cosine of 3 pi over 4. I hope one of you just kind of shouted at the screen and said, "No, Mr. Jurashek, you're wrong," because I was wrong. So 6 times the cosine of 3 pi over 4 equals x. You also remember that that's the formula. That's literally the formula of r cosine theta equals x. Cool. So we pull out our calculator, and let's see. We're gonna get to graphing it later, but we'll just make sure we do this correctly. So I want to make sure I'm in radians. I want to be in radians. That's important. And then, how did I get all the way up there? Okay, we'll do 6 times the cosine of 3 times pi divided by 4 is negative 4.2. Cool. So this would be equals negative 4 points, let's say, for the sake of accuracy, we'll say 243. Okay, and so that's negative 4.243. And let's see, for y, we can do the same thing. We can do r, the radius, times the sine of theta. The radius times the sine of theta equals y. And before we get to that, though, I want to make sure I don't, maybe it's my ADD inside of me, but I want to make sure that I don't, that I cover all my bases here. If you were the person who decided to do 6 cosine of pi over 4, 6 times the cosine of pi over 4, just want to show you what that looks like. Pi divided by 4. It'll get you the same number, but it will be positive. And the reason why, because it assumes that you're doing pi over 4, which is pi over 4, I think if you're seeing this right, I hope it's not backwards for you. It's pi over 4 from the unit circle, so that'd be like, it would look like a positive angle. So if it was a it kind of thinks you're using a positive angle and it's all in the first quadrant, but it's not. So you just got to kind of, that point is, that works too. Whatever you want to do is fine. But you just got to remember that it's going to be negative no matter what, because it's on that left side. It's in the second quadrant. Okay, y is, let's see, y is r times the sine of theta. So I'm just going to go ahead and use 3 pi over 4 again. So it'd be 6 times the sine of 3 pi over 4. And we've got 4.242 again. Great. So that means this is 4.24. So that means that this y equals 4.243. And that is our answer. That's all there is to it. And we're done. All right, cool. If you wanted to do it the normal way, without a calculator, and if you want to use if you want to use a unit circle, there's probably you can get an even more exact answer, and the computer and the problem might actually ask for exact answers. And if that's so, no problem. We just gotta pull a unit circle. So or just remember the unit circle. That works as well. So cosine of 3 pi over 4 is negative square root 2 over 2, and sine of 3 pi over 4 is square root 2 over 2. So if we multiply that by 6, so r times the cosine of 3 pi over 4, or 6 times the cosine of 3 pi over 4, would be 6 times square root of 2 over 2, would be negative 6 times the square root of 2 over 2, which reduces down to negative 3 square root 2. And then same thing with 6 sine. So I multiply that answer, 3 pi over 4. If I multiply the sine of 3 pi over 4 by 6, multiply the whole thing by 6, which is square root of 2 over 2, that'd be 6 times the square root of 2 over 2, which reduces down to 3 times the square root of 2. So that might actually be what the computer's looking for more accurately. So that may be a preferable answer, and so that's what you're looking for. That's how to do it. Great, move on to the next problem. We're gonna have time for one more problem before a break. Plot the point whose polar coordinates are given. This is fairly straightforward. So we'll go make our axes. We'll go 240 degrees. That's a little bit less than 270 degrees. Let's see, 240 degrees. It's about 30 degrees before 270. So we'll kind of draw this, and you might want to just kind of estimate there that is that direction. So that's 240. Let's see. So this is supposed to be about 60 degrees, right there in that center here. This is about 60. This section over here. And then we're gonna go, when it says we're gonna go -3. So remember what -3 means. It means we're going backwards. We're going back the opposite direction where we came. So instead of going forward, we're actually gonna go backwards. So we'll go backwards 3. Excuse me. To this point right here. So this point right here is the point -3, 240 degrees. Cool. And that is our answer. That's all we have to do there. And it looks like we are just about out of time, so I will see you after a quick break. Thanks for working hard, you all. All right, got some hot chocolate and I'm ready to get back into it, yeah? All right, so we've used an algebraic method to find the rectangular coordinates of the points with the given polar coordinates. Approximate the exact solution values with a calculator when appropriate. Okay, so let's break it down to what it's saying here. It says use an algebraic method to find the rectangular coordinates of the point with the given polar coordinates. So we're trying to find the rectangular coordinates of the point, which this point that has polar coordinates. This point. Okay, and that's really what we're doing, trying to use algebra to solve it. So we got 4.6 and then 4 pi over 3. So our formulas, as you may remember, is x equals r times the sine, r times the cosine of theta, and y equals r times the sine of theta. And so we just kind of plug those in, and but really all we have to do, we're done after that. So let's go ahead and do that. So x equals the radius, which is 4.6, because it's now in radius theta mode. and 4.6 times, 4.6 times the cosine of theta. And theta is 4 pi over 3. 4 pi over 3. Okay, now what is 4 pi over 3? That's definitely, that 4 pi over 3 is actually 240 degrees. So we can just plug that in. 240 degrees, as you may know, is, let's see, 240 degrees, or 4 pi over 3. The sine equals, let's see, negative root 3 over 2. And the cosine equals negative 1/2. Okay, so we'll just kind of work with that. So x equals 4.6 times negative root 3 over 2. No, sorry, x times negative 1/2. Negative 1/2. And then for y, we know that y equals 4.6 times the sine of 4 pi over 3. And so, let's see, that equals, y equals 4.6 times, let's see, negative root 3 over 2. So that'd be negative root 3 over 2. And we just kind of calculate from here. 4.6 times negative 1/2 would be negative 2.3. So x equals negative 2.3. And then for y, well, let me get my papers in order here. For y, that'd be 4.6 times the root 3 over 2. So we can't really do that with our minds using root 3. So we're going to just plug those numbers in, and let's see. We will get. Let's see, that's 4.6 times. Let's see, square root. 4.6 times square root of 3 divided by 2, and there's actually a negative in front of that, so I'm going to insert the negative. Actually, don't forget that. Syntax. Oh, I put the negative in the wrong place. Times negative. I need to, oh, it doesn't delete it automatically. That's strange. It might be in insert mode. And so that gives me negative 5.633. So this is negative y equals negative 5.63. Is that, do I round the 3? That's a, yes, no you don't, yes you do. So you round the 3. 3, 4. So these are the coordinates. So I guess more accurately, we'd finally put the answer as negative 2, negative 2.3, and negative 5.634. And that is our answer, just like that. Cool. Let's see. So that's that answer. So now we convert the polar coordinates of negative 3 to negative 270 into rectangular coordinates. Yes. So this is the exact same procedures. We've got polar coordinates. We need to make rectangular coordinates. So we can just use x equals r times the cosine of theta, and y equals r times the sine of theta. This one will be a little bit, actually it's not, it's the same thing as before. I had to do something pretty strange here. Well, it actually does do something pretty strange. So we've got 270 degrees. So we get negative 270 degrees. So what is negative 270 degrees? Do we have negative for the last one too? No, I was positive. Otherwise I've been up a creek for a second to redo this video. Negative 270 degrees. So I think about that. That's not what you normally think it is. That's you think 270 degrees is this. So negative 270 degrees would be negative 270 degrees would be this. That'd be negative 270 degrees. So that's actually 90 degrees. We're going 90 degrees, and we are trying to find the rectangular coordinates of 90 degrees, and you go negative 3. So that's negative 1, negative 2, negative 3. And so instead of going upwards, this is normally the direction we would go, but we're going to go down 1, 2, 3. So negative 3. So we got this point down here. So we don't even have to do algebra here. Remember, we just can look at it and say, okay, that's the answer. This value, let's see, that's 0, negative 3. That would be our answer. That's legitimately just all the answer is. Cool. All right, so let's see. Did I plot it? No, I don't have to plot anything. Okay, and that's all the answers. So let's move on to the next problem. So that's our answer. Sorry, I'm kind of all over the place right now. Let's look at this next problem. The polar coordinates of point P are given. Find all of its polar coordinates. Oh, find all of its polar coordinates, excuse me. Yes, so we have 2 pi over 3. So 2 pi over 3. We're trying to find all the polar coordinates of this. To do that, we're going to have to remember what our equation is for polar coordinates. We'll go all the way up here to find all the polar coordinates. We said we can find all the polar coordinates if we look at this equation right here. So I'm going to go ahead and copy this. Let's do copy. And then I'm going to get back out, move back down. All right. So let's see. This, we're going to paste that in right there. Great. Okay, so all our polar coordinates are essentially that. We take the radius and theta and just plug it in, and that's our answer. Great, so our radius in this equation, our radius equals 2. Our theta is pi over 3, because this is the radius, this is the theta. And we just plug it in, and we've got all the possibilities. So we've got the radius so we got 2. And then, oh, put it in purple, that's interesting. I didn't know that. 2, sorry, I'm just talking to myself here. And pi over 3 plus 2n pi. That's one set of all the options. Because remember, that's the 2 pi over 3, and then I could rotate 2 pi as many times as I'd like, as many n as I'd like in order to get there. I could even rotate negative n, and that would work too. So any n, sure. But I guess I couldn't do half of n. I couldn't do like 0.5 n, because that wouldn't work. So let's just make the specification that n is an integer. N is an integer. Because if I did 1/2 n, if I did 1/2 rotation, 1/2 n, that would give me here, and I don't want that. I don't want to do 360 degrees plus 1/2 360 degrees. Anyway, so that's one of the options, and I plug it in over here. So that's 2. Oh, excuse me, this is negative r. Negative 2. Did I copy over? Oh, I hope I put it in right. Negative 2, and then pi over 3 plus pi plus 2n pi, where n is an integer. So n is an integer. Great. And that is all the possibilities. So I could go pi, could turn pi, and then go backwards, negative 2. That's also an option. So those are all our different options here. And that's our answer. Simple as that. You just kind of plug and chug there, as long as you have the formulas. Okay. The rectangular coordinates of point P are -2, 5. Use an algebraic method and then approximate exact values with a calculator when appropriate to find polar coordinates of P that satisfy the following with A, B, and C. Oh, there's 3 things here, so it looks like it's going to be a pretty messy problem. Did I not turn this? Oh, excuse me, I'm sorry. I'll have to close this a little bit early. If I find out, I'll just, maybe half the time or so. I'm already off my game. So we need to find the rectangular coordinates of P are 2, 5. Let's start with that. So we got -2, and then 1, 2, 3, 4, 5. Great. So we need to use an algebraic method and then approximate exact solution values with the calculator when appropriate to find all the polar coordinates that satisfy those. Okay, so let's remember our formulas. Actually, I'm just gonna make sure that this is, oh, it's not there. Let me just add it there. Okay. Sorry, I'm gonna have to probably edit that audio or something, or put in a comment or something that there's just be a negative next to that R. Okay, there is all of this, and we're going to copy all this. These are our tools to find things algebraically, and these will become really helpful to us in this specific problem. We're just going to paste that in here so we don't lose it. And let's make sure I'm blue. For some reason I pasted in purple last time. I like pasting in blue because that kind of shows the color. Okay, because blue is like we need to focus on this color. This is the notebook color. Anyway, so we need to find, in order to find the coordinate, a coordinate, remember, is r and theta. We need to find a radius and a theta. And we can find either one first. Now these equations over here, we can use x and y, but that helps you find r and theta. We can only find one of them right now because we don't know either of them. So we're gonna try to plug things in to try to find at least one. Fortunately for us, we can find r if we plugged x and y into here, because we know what x and y are. We could find r, use the Pythagorean theorem. We could also plug x and y into here, and we can use the inverse tangent and find theta. So either way, we can find one or the other. Let's start. I'd recommend, I think the easiest is just to use the Pythagorean theorem and use x and y to find r. That's probably the most helpful as well. So let's start to find the radius itself. So the radius is, let's see, if our values are -2, 5, -2, 5, that's the rectangular. So that means that we have -2 squared plus 5 squared equals the radius squared. All right, so that means 4 plus 25 equals the radius squared, which means that 29 equals the radius squared, which means the square root of 29 equals our radius. Great. Now you might remember that it's not a negative. Well, you might notice that I'm not using a plus or minus squared, negative squared 29. Because remember, if we had a negative radius, we'd run into problems. And so that's not the case. This is just a positive square root of 29. If we had a negative square root of 29, it would go in the opposite direction, and we don't want that. Like, we also don't want to erase our entire axes. Yeah, so we don't want to go in the opposite direction. Oh my, what is going on here? Excuse me, I'm sorry. That's the next problem. Okay, so we know this is the square root of 29. Now we can figure out what that angle is, and then we can figure out all the possible angles. There's a bunch of ways we could do this. Now that we have the graph, we can just start looking at graphically and try to use the Pythagorean theorem and let's see, we have a whole bunch of tools at our disposal. However, I think what we're going to do here, we could say negative. We could say this is that the x coordinate is -2 and this is 5. You can work from there and figure it out. Let's just use the formula to figure it out though. It says use an algebraic method, so we'll use the algebraic method. Tangent of theta equals y divided by x. So y divided by x would be 5 divided by -2. So tangent of theta equals 5 divided by -2. And let's see, so that'd be -2.5. -2.5. And so the question is, can you think of anything that any options that would give you -2.5? And if you look at your inner circle and try to figure out which ones you can find, let's see. Is there anyone that actually works? I don't think there is anyone that actually will give you -2.5. So we have to find this a different way. We just kind of have to run with our calculator, I suppose. So we'll go ahead and pull out the calculator, because I don't think there's. Maybe I'm wrong. I could be wrong. We'll go into degree mode because I like having degrees just to kind of get me started. But you want to eventually put this in radians. It looks like the answers will all need to be in radians. Because let's work with this for now. Because you can use degrees to get very exact degrees, but then radians is always something in terms of pi, and so the calculator will always give something approximate for radians. It'll be if it's pi over 2 is the radians, it'll give you half of pi, and that's just a long decimal. But if it's 90 degrees, it'll just give you 90 degrees. So I like that. Gives you a more exact answer that way. Okay, so we have inverse of tangent. Let's see, theta equals the inverse tangent of 2.5, or -2.5. So let's see if this actually works. This might be outside our domain. Hopefully it'll work. Of -2.5 to 2.5. Not, oh my goodness. I am so sorry. I'm getting across. I'm getting across here. Okay, so that's 68.198 degrees. Okay, so that's really not so helpful for us as far as like degrees go. So I'm just gonna go ahead and put it back in radian mode and find the radians. Okay, because radians are helpful. So radians are what the answer needs to be in. I think degrees are more helpful, but radians are we in. So we need, it's -1.5 0.190 radians. Okay, so let's see. We have 0 so for A, B, and C, we need to find. Well, let's start with this. Oh, man, I really do have ADD, don't I? That's what they said. That's what the doctor says. So, we go a radius of square root 29, and we go a radius. The theta is negative 1.19. Is that a 0? That is not a 0. That is a, yeah, it's a 0. That's a I'm rounding down to 0. Okay, so that's our coordinate. That's 1 point. Now we need to find all the options, all the versions of that point that are between 0 and 2 pi. Okay, so let's see. Let's remember how we can find different versions. That comes over here. We can find different versions of a polar coordinate by taking the radius and adding 2 pi to it. Let's say taking theta and adding 2 pi to it a certain number of times. And then we can take negative the radius and then do a negative 2 pi. Okay, so here's what this looks like. We're going to paste this in. Go ahead and paste. Okay, so you've got the radius. And so we could take 1.190 and we can add 2 pi to that. So we can say we have the radius. If we have, oh my goodness, we have the radius and we have negative 1.190. We can add 2n pi to it. Okay, so the radius is root 29. So every single one of these combinations are valid possibilities. So let's see what possibilities we have if we add 2 pi. And I'll just kind of add several cases of them. Because we need something that's between 0 and 2 pi. That's what we're looking for here. So we get negative 1.19, and we're going to add 2 times pi, and that gives us 5.0. Let's see. I'm trying to find between 0 and 2 pi. I'm trying to find a theta that's between 0 and 2 pi. That's what A says. A says we need to find something between 0, a theta that's between 0 and 2 pi. Now, is 5 between 0 and 2 pi? It's greater than 0. But is it less than 2 pi? 2 pi is 6. So it's between 0 and 6.2. So that means that it isn't 2 pi. Okay. So for A, let's kind of make a new section over here. A, one of our options is root 29. And then 5.093. That's a valid way of going about this. Another one, let's see, if we added 2 pi again, would that still work? It probably shouldn't. So if we have 2 pi, if we add 2 pi again, add maybe 2 pi, that's another way of thinking about it, that gives us 11. That's beyond 6. So that won't work. So that we've exhausted all the possibilities for that first route of between 0 and 2 pi. Now there's another option. We have that negative r. We add 1 pi and then 2 pi. So if we start with negative r, negative root 29, are there any possibilities there? Negative root 29. Let's see, our initial theta was negative 1.19, and let's see, if we add pi to that, is that between 0 and 2 pi? If we add pi to that, that gives us, no, not pi times pi. Oh my. Is 1.951. Oh, that's between 0 and 6. So that would work. I hope that maybe this is still confusing. We're trying to find theta where 0 is less than or equal to theta and 2 pi less than or equal to 2 pi. And we know 2 pi is the same thing as 0 is less than or equal to theta, which is less than or equal to 6.2. Yeah. Okay. So, and we found that this answer here is 1.951, and that is between 0 and 6.283. So we can include that one, 1.951. Now, if we add 2 pi on top of that, will that work? If you are thinking carefully, you might realize that is probably not. That doesn't make any sense. And then, yeah, we can see it goes to 8. So that'd be outside of our range. So these are all of our possibilities for A. So that's our answer for A. For B, we have, what do we have for B? We've got, we need to find between negative pi and pi. Okay, so let's see. Let's change colors to I guess purple. Or I've used purple so many times. Let's use yellow or blue. There we go. Okay, so B, negative pi to pi. So negative pi to pi, that'd be, let's see, that would be from negative pi is negative 3.14. Negative 3.14 is less than or equal to theta, which is less than or equal to 3.14. Okay, let's see what options we have for here. Let's see if we have any options for the square root of 29. Let's see. Let's look at our first option. Our first route is negative 1.19. Well, that's in between. Yeah, that's between negative 3.14 and 3.14. So that's negative 1.19. Yeah, that'll work. Great. So we already have an answer there, because negative 1.19 is between these two boundaries. Now, of course, if we add 2 pi or subtract 2 pi, as we've seen with the previous problem, that won't actually get us, that'll get us beyond the values of 2 pi. That'll get us beyond negative pi to pi, because you're adding 2 pi. You're adding 2 pi. You're just going outside the boundaries. The boundaries are, if it's going from negative pi to pi, that's only a size of 2 pi. So if you add 2 pi, you're going to go outside that boundary. Okay, let's see if we can find it for a negative 29. Okay, so let's see. If we add pi to this, if we take that negative, if we take the negative 1.9 and we add pi, that gets us 1.951. So that works out. That works out great. So it's 1.9. That is between negative 3.14 and 3.14. So that works out great as well. That's 1.95 and 1. This is a 0 on this end. And so that also works. That works out great. And again, if we were to add 2 pi on top of that or subtract 2 pi from that, it would not work. So these are our only options here. Let's look at the third one. Now for the third one, I'll use this red. So C, the range for C asks us from 0 to 4 pi. Okay, well we know it's going to be, everything from 0 to 2 pi will work, so everything from A is going to fit in, because 0 to 2 pi is inside 0 to 4 pi. So we'll put that in there automatically. We will get, let's see, we'll get from 0 is less than or equal to theta, which is less than or equal to 4 pi. And let's see, 4 pi, before we get too far into this, 4 pi is 12.566. So 0 is less than or equal to theta, which is less than or equal to 12.566. Great. So we'll go ahead and, so if it's, we got to figure out those values in between. So 0, for the first one, we know that these values here, root 29 and 5.093, that works because that's already in the value. So we can just copy over everything from A, from letter A. So 5.093, that works. And then we can also say the negative version, negative root 29. I'm putting a space in there because I think there's probably going to be another one. Because I'm thinking if you add 2 pi, that's still going to be inside the range. Okay, it's still going to be inside the range of 4 pi. So let's look at it though. So we got 5.093. That was a little bit before. So we take 5.093 and we're going to add 2 pi to it, and we'll add 2 pi, and that gets us 11.376. That's less than 12.566. That also fits. You can imagine that if I were to add 2 pi again, then that would not work. Okay, that's rounds down. Yeah. However, if I was to take this and subtract 2 pi, let's clear this. Let's take this and what? If I was to take this and subtract 2 pi, it's probably, oh, it's length, yeah. Oh my goodness, excuse me. I just don't know how to run a calculator, apparently. Apparently I don't know how to use calculators. Okay, so I'm gonna go back to the original answer. Oh, it's just running, it's too small. So if I subtract 2 pi from it, Yeah, 2. I must just be, either I'm tired or I don't know what I'm doing. There we go. You have to take the whole thing and subtract 2 pi. That's negative 1.19, which is also outside the boundaries. So you could be subtracting 2 pi as well, but you can kind of see that if you subtract 2 pi from any one of these, it's from any one of the things that are less than 6.1 or 6.2, then it's not gonna, it's gonna be negative, and the negative is not what we want, because negative is less than 0. Okay, so let's see, the negative root 29 and then 1.951, we can take that. So we can take, oh my goodness. So yeah, we'll take this. Oh, it's just running out of space is all it's doing. So all of you in the room who are screaming that, that's exactly what's going on. So okay, so if we add 2 pi, so 1.951, we get 8.234, which is also less than 12. So that works great. Negative root 29, and then 8.234, and that rounds down, so that's good. If I were to add 2 pi on top of that, then we'd have problems. Is that right? Yeah, we go 14. 14 is larger than 12, so that's outside our boundaries. But these then are our answers. These are exactly what we're looking for. And yeah, great. So that'll move on to the next problem. Actually, I can just box these out just to make sure that we know what we're talking about. These are the answers. All right. The next one says to use the grapher to match the polar equation with its graph. And this will be interesting. This will be kind of fun because I think we're gonna actually get to the actual polar part of our calculator. So that'll be really nice. We're gonna look at, if you go back to mode, there's 3 modes. If we click on polar, now when you go to, if you go to the polar mode instead of function or parametric, you click on polar. Then you go to y equals. You'll see that instead of having y equals something or x1 and y1 in parametric, we have r equals something, the radius. This is the standard form for writing equations in the polar coordinate system. You can do some pretty fancy things if you write equations in terms of the radius and theta. So it's really cool because in the same way that we can have like functions in terms of y and x, we can have functions in terms of the radius and theta. As theta moves, what happens to the radius? You can see what kind of designs we can make. We can make these really neat, fancy designs. In fact, let me just show you kind of what kind of things we can make with it. Well, actually, I don't want to waste your time. But you can see, yeah, as radius as theta increases and decreases, you can see how it changes the radius of the equation. So, for example, if we put 4 times the cosecant of theta. Now, cosecant is 1 over sine, so we'll do 4 divided by the sine of theta. And now you'll see that when you hit the x, t, theta, n button, it'll actually put in theta because we're using a polar equation. I think that's cool. It's working out for us. We hit graph and zoom in so that you don't overwhelm yourself from your infinity graph there before. You realize, okay, that right there is just a straight line. Okay, so that is this over here. That goes there. All right, simple as that. But oh man, last year I went all into detail about the why the rose pattern happens the way it does and why circles happen the way they do. I'd love to get into it, but I don't want to waste your time either. So if you want to know more about this, please let me know. I'd love to make a video on why this works, why this relationship between the radius and theta is. But I also don't want to waste your time. So just let me know if you want to see it, and I'd be happy to make a video on that because it's really cool stuff. It's fascinating how this comes about. But let's move on to the next one. The next one says 32 says 3 times the sine of theta. 3 times the sine of theta. You just plug it in and it'll give you the answer. So it's saying that as theta increases, if we graph all of theta, if we graph all the different values of theta, we'll get this really neat circle here that starts at 0, because sine starts at 0 and it goes up to 1 and it goes back down to 0. Anyway, I'm getting beside myself. Kind of getting out of frame here. But yeah, that's the so that circle is this one. So if we go back to the calculator, we go to 5 cosine theta. 5 cosine theta. And that gets you, what does that get you? Well, it gets you this neat sideways. Oh, 5 cosine 3 theta. See 3 theta, excuse me. I didn't see the numbers there. Maybe it's because of my lighting. Maybe it's because I need to go do other things. There we go. So that gives us this really cool rose pattern with 3 theta. So let's see, you see that one coordinates to this one. And we'll go ahead and go to the last one. You can probably tell the last one will be that other rose pattern. And we're just going to plug it in to confirm it. This would be 5 sine 3 theta. And we'll hit enter. And that gives us, yeah, because what we're looking for, that fancy sign. So we'll just plug this in. And that's how you do it. You just plug it into your calculator and you're done. It'll give you exactly what you're looking for. Again, make sure you are in, your mode is polar. And I don't believe it matters whether you're in radians or degrees. I think if you're in degrees, it'll do this. No, actually, if you're in degrees, it'll be awful. Never mind. If you're having trouble, use radians. Let me make a mark up there just in case someone's hasn't watched that part of the video and has forgotten and hasn't seen it. Use radians. Use radians. Okay. Right, because if you use degrees, you went from 0 to 360 degrees. It does something very different. It launches up real fast. Or actually probably launches up real slow. And then you run out of bounds real quickly. Anyway, again, that's for another video. Okay, the next problem. Convert the polar equation to a rectangular equation. Then use a rectangular coordinate system to graph the rectangular equation. Yes. So convert the polar equation to rectangular. That's the first step. And then use a rectangular coordinate system to graph the rectangular equation. All right. We'll start with the rectangular coordinate system and just we'll turn it into a rectangular equation. So we remember our ways to convert from one thing to the other. Remember that r cosine theta equals x, r sine theta equals y, and then x squared plus y squared equals the radius squared, and then tangent of theta equals y over x. Great. So from here, all we need to do is if we can match any one of these things, if we can match like r cosine theta, if we can make like an r cosine theta or make an r sine theta, then we'll have an x or y. If we can get an x, if we can get a radius squared, we can convert that to x squared and y squared plus y squared. Or if we can get somehow manage to get tangent of theta, we immediately can replace that with y over x. So trying to do that to convert is everything, all the thetas and all the radiuses into x's and y's. So you have no longer a radius and theta, but you have an x and a y. A lot of words. Simple thing. The simple answer is let's mess with it so we can see if it matches up with an equation. So secant theta, that doesn't match anything. But remember, what is secant theta? Let's see. Radius is times 4. Let's see. Secant of theta is 1 over cosine. So that's 4 divided by the cosine of theta. I should write things in the appropriate direction. There we go. 4 times the cosine of theta. Oh, so if we can get r cosine theta, then we have x. Great. And we can do that. We can multiply cosine theta on both sides and get r cosine theta. So we'll multiply cosine theta times r cosine theta times all of that. These cancel out. We get, well, honestly, r cosine theta equals 4. And, well, there we go. So r cosine theta, that is x. So we will say x equals 4. And that actually is the answer. If you were to graph r cosine, if you were to graph the radius equals 4 secant of theta, you would actually get the same line as x equals 4. That straight vertical line at 4. Okay, and it says then use a. So this is the first answer. This is 1. Oops, this is 1. And it says then use a rectangular coordinate system to graph the rectangular equation. Okay, so we use. Well, if we were to go to a graph, we go 1, 2, 3, 4, and we can actually just graph it. So that's let's use the purple. Yeah, this would be, if not that, this would be, that'd be the equation. This is x equals 4, and it's also r equals 4 secant theta. That is the equation. All right, and that's the graph. And you can confirm that by graphing that yourself and seeing that that's exactly what that would be. I encourage you, go ahead and try graphing 4 secant theta. You'll see that it actually is this. It'll just graph that straight line. All right. All right, so it says to transform the polar equation to an equation in rectangular coordinates. Identify and graph the equation. Okay, so the polar equation, let's see, so transform the polar equation into an equation in rectangular coordinates, that's step 1. And it says identify that equation, and then graph that equation. Okay, great. So 3 things. And we're going to use the same steps as from the last problem. If you were there for the last problem, we're going to do x equals r cosine theta, y equals r sine theta. Let's see, we've got x squared plus y squared equals r, and we've got the tangent of theta equals y over x. Okay, so we need to transform this more and more into like those, and use whatever we can to try to convert it into all x's and y's. We got r secant of theta equals 3. This could be daunting at first. Let's try to break it down. So what is secant of theta? Secant isn't in sine or cosine, and there's not really an easy way to convert it to tangent. Technically, sort of there's a way, but it's a bit difficult. Let's see if we can change it into something else. Let's see, secant is 1 over cosine. So we can say this is r divided by the cosine of theta, because 1 over cosine is just dividing by cosine. Let's see, or we could say r times 1 over cosine, which is the same thing as r divided by the cosine of theta, and that equals 3. Okay. Now, let's see, what else can we do? We do have a cosine of theta on the equations above, but it says x equals r times the cosine of theta. That's not exactly what we're looking for, but maybe it's still workable. Maybe we can still do something with it. Let's see, because if we had r cosine theta, we could just convert that to x. We don't have x. We have r and we have cosine of theta opposite each other. So let's see if we can solve for cosine of theta and see what we can do there. If x equals r times the cosine of theta, then the cosine of theta, that's something else. Cosine of theta equals x over r. Great. So if cosine of theta is x over r, I can't get rid of r yet, but I can still replace cosine of theta with something. I can replace with x over r. So let's try that. R divided by x over r equals 3. Well, that works out conveniently, actually. That works out very conveniently. Let's look at this. So r divided by x divided by r, this becomes, that is the same thing as saying, r times, that's the same thing as saying r over 1 times x over r. And, no, that's, yes. No, it's yes. Did I do this correctly? Cosine of theta, let me make sure I'm doing this right. Yes. So cosine of theta is x over r. So if that is x divided by r, we can multiply. Yes, we can multiply it like this. It would actually be a little bit different. We'd say this would be, we take the inverse, so r over x, and the reason why, just if you're at all curious, if you're all confused by what just happened, this is the same thing as r over 1 divided by, this is the same thing as r divided by x over r, which is the same thing as saying r times r over x equals 3. Okay, so we get, let's see, r times r divided by x is 3, so that gives us r squared over x equals 3. Oh, that's progress. We can do something with that. So if I bring this over to the right, that gives us r squared equals 3x. I just brought the x to the right because I think it might be easier, because I'm looking at this r squared. I know what r squared is. If you know this equation up here, x squared plus y squared equals r squared. Excuse me, this would be r squared. We can replace r squared with x squared and y squared, and we'll be done with it. So we'll say x squared plus y squared equals 3x. Very, very good. Okay, so if that is the case, which it is, we can say y squared equals negative x squared. I'll bring the x squared over so they're all together, plus 3x. Okay. So let's see, what kind of graph is that? It looks kind of like a quadratic. It also looks kind of like a circle, if you think about it, because these are the equations of the circle. But you'll notice that the radius is 3x. The radius varies depending on how far out you are. So if you go further out, the radius will get bigger. So, which kind of makes it look more and more like a quadratic. Let's actually just graph it just to see what it is. So let's go back to our normal equation, our function, and let's say we graph. Let's graph both of these. So we'll say this would, if we graph this in function mode, that means that y equals the square root plus or minus the square root of x squared, negative x squared plus 3x. And so that gives you this. So let's start with the square roots of negative x squared. I'm now in function mode if you missed it. X squared plus 3x. And we will do negative square roots of negative x squared plus 3x. There we go. Is that right? That's right. So we graph that. That gets us, this. So it looks kind of like a circle, but also looks kind of like an ellipse a little bit. Oh yeah, that's got to be a circle. So even though we've got that 3x in there, because we got that x squared and y squared, that trumps it all. So it's still the equation of a circle. Maybe it's sort of an elliptical circle, but definitely a circle. Yeah, that's definitely more of an ellipse, because 3 is, if I was to make it more rectangular, if I was to make this more accurate, this would be more appropriate. So this is definitely an ellipse. Cool. This is an ellipse. So that's step 2. This is step 3, and this is, this is step 1. This is step 2, and the last one is that graph is the ellipse. Great. All right. And it looks like we're out of time. So I guess it's time for a break. Welcome back. Over the break, God graciously raised the sun for me to give me better lighting. So that's pretty great. What actually happened once, Joshua, son of Nun from the Bible, he asked God to keep the sun still so he could fight. And we actually just asked the world. He said, "Oh, sun, if you could stay still." And that was the one time in all history where just a mere mortal, a mere human, commanded the world to do something, and it just obeyed. So, anyway, that's fascinating stuff, but that's not why we're here. We're here for this problem here. It says convert the rectangular. Oh, I want to get this started. My hot chocolate has turned to a smoothie. It says, let's look at the problem. Convert the rectangular equation to polar form. Then sketch the graph of the rectangular equation. Okay, so we've got 2x minus 3y equals 7. And we know our equations, the equations we have at our disposal, are x equals r cosine theta, y equals r sine theta. Let's see, x squared plus y squared equals the radius squared, Pythagorean theorem. And finally, the division, tangent of theta equals y divided by x. Okay, these are the 4 tools we have at our disposal. And, well, we don't really have x squared and y squared. You might be able to try to manipulate something so you can get x squared and y squared, maybe by squaring both sides. There's no way we're dividing y by x. I mean, you could kind of try to make that, or we could just kind of leave it as is. And honestly, the easiest thing to do is say, hey, we've got an x, let's turn that into r cosine theta. We've got a y, let's turn that into r sine theta, and just kind of work from there and see what happens. Maybe we'll run into a wall, we'll have to try something else, but this is a great first place to start. So let's try doing that. let's try just using the bare bones to say, hey, we've got an x, we've got a y. Let's just convert them to r cosine theta and r sine theta. So that gives us 2 times the, let's see, x is now r cosine theta. So x becomes that, minus 3 times r sine theta, which becomes that, and that equals 7. Great. Okay, so now we need to continue to make this in a rectangular equation. All right, so there's, let's see, a normal rectangular, sorry, we need a polar equation. A normal polar equation is something where, in the same way that a rectangular equation is often y equals something in terms of x, the polar equation is r equals something in terms of x. So in other words, we need to solve for r. A polar form is r equals something, whereas a rectangular equation usually is y equals something or something like that. Or in this case, 2x minus 3y equals 7. So let's try to solve for r. We can factor out an r on the left side. And we get r times 2 cosine theta minus 3 sine theta equals 7. Great. And then just divide both sides, and we get r equals 7 over 2 cosine theta minus 3 sine theta. And that's the answer. That's all there is to it. We solve for r, we made an equation, and all we have is theta and r as our variables instead of x and y. And we solve for r. So that's it. We're good. We've got the answer. Cool. This next problem asks us to convert the rectangular equation to polar form, first of all. Let's try to, oh, before we get to that, I didn't even finish this problem. Oops, sorry. We need to sketch the graph of the rectangular equation. The graph of the rectangular equation, this is if we want to try to graph the rectangular equation, that's much easier than graphing this weird polar equation. So let's look at the rectangular equation. We got 2x minus 3y equals 7. Let's do that. This is step 2. First one is step 1. Okay, so for step 2, I'll use green. We got 2x minus 3y equals 7. Actually, yeah, that's fine. And what we want to do is we want to graph it. So I'll put it in slope-intercept form to help us graph it better. Let's see, so we'll do, that equals negative 3y equals 7 minus 2x, and then y equals 7 minus 2x divided by negative 3. Or in other words, in full slope-intercept form, we've got y equals negative 2x over negative 3 plus a 7 over negative 3, which reduces down to, let's see, y equals 2/3 x minus 7/3. All right, that's the slope-intercept form. And just as graph that equation, we can do that. We will start by graphing the intercept as is normal. Hopefully I can make straighter lines one day. Oh my goodness, that's not a straight line at all, but it'll do. We'll work with it. So we've got, let's see, negative 7/3. That's negative 2 1/3. So because 6/3 would be 2, negative 2. So we got negative 7/3. We start right about here, and we rise 2, run 3. Let's say rise 2, rise 2, run 3. So something like that. This should be a little bit higher. But you get the idea of what we're trying to do here. Let's kind of actually, let's erase this because that's in a way. All right. So we rise 2, run 3. There we go. And we can just go ahead and graph that line just like that. I'm telling you, sometimes I'm doing this and I really feel like Bob Ross, just trying to paint a line or something. Okay. So, and that's the answer. That is the answer there. So now we can actually move on to this next problem. All right. Convert the rectangular equation to polar form. Sketch the graph of the rectangular equation. Don't use a grapher. And then support your hand sketch by graphing the polar equation with your grapher. Okay, a few steps here. First of all, it says convert the rectangular equation to polar form. That looks like the first thing to do. Secondly, we need to sketch the graph of the rectangular equation. Don't use a grapher. So that's the second step. The third step is support your hand sketch by graphing the polar equation with your grapher. So we're going to graph the polar equation. Great. All right, so convert the rectangular equation to polar form. Let's start there. So let's get our tools back up. So we've got x equals r cosine theta, y equals r sine theta. We've got, let's see, what was the next one? That's x squared plus y squared equals r squared. And we've got tangent of theta equals y over x. Good. All right, so we need to convert these to polar form. And again, we don't have an x squared and y squared. We don't have y over x. We kind of could try to find x squared and y squared, but you'll quickly find out if you do that for this problem, it'll get really messy and it won't actually get you what you want, because you may end up with an x squared and y squared. If you're thinking ahead on this problem, you've already tried it. You make an x squared and y squared, but you also get like 3x. You get 3x and or maybe like 6x and 4y, and it just leaves a lot left to do. So it actually makes more problems instead of less, because then you've got another x and a y that are hanging there. All that to say, this x squared and y squared isn't really helpful right now. What we want to do is we just want to do the basic intuitive idea. Well, maybe not intuitive, but the simplest things. Try the simplest thing first and see what happens. We'll take the x and the y, and we'll just replace x with r cosine theta and y with r sine theta. So that's what we'll do. We will take, this will be r, oh hello, okay, r cosine theta. I hope it's not this recording, because that would be bad. R cosine theta, let's see, plus 3 squared plus, let's see, it's r sine theta plus 3, or plus 2 squared equals 13. Okay, so we've kind of gotten somewhat, we've got it all replaced with r and theta, but now we need to solve for r. So we need to solve for r equals something. That's kind of what the polar form is. So let's do that. We get, let's see, if we reduce this down, we get r squared, let's see, r squared cosine squared theta. Let's see, that's the first, and then we get plus 6 r cosine theta plus, let's see, that'd be 9, no, yeah, 9, 3 squared. So I just did a quick a plus b squared formula there. And then for the next, that's another a plus b squared formula. So that'd be r squared sine squared theta plus, let's see, that'd be 4 r sine theta, and then plus 4 equals 13. All right. So let's see if we can solve for r here. Let's kind of simplify this down first a little bit so we can kind of make more sense of it. Let's see, this 9 and 4, I'm going to try to simplify it a bit. The 9 and the 4, that's just 13. Those combine to be 13. Is there anything else we can combine? I'll try to regroup things so it kind of looks a little simpler as well. So we get r squared cosine squared theta. And then we have, let's see, we have r squared plus r squared sine squared theta. Okay. Well, that looks promising. You might be able to see something promising there. Maybe not, if not, that's fine. And then plus 6 r cosine theta. And we did plus 4 r sine theta. Plus 13 equals 13. Okay. Well, great. Well, one of the easiest things we can do is we can say that these 13s, we can subtract 13 on both sides and just get rid of the 13s. So subtract 13, subtract 13. That makes both of these zeros. So that's pretty nice. What's something else I can do? Well, to try to simplify this a little bit. Well, since the right side is 0, I can divide by anything, and the right side will still be 0. So that's fortunate. Let's think about this. I can actually factor out. Maybe that'll be helpful. Maybe if you factor out an r, that might be helpful. If not, here's something we can do. Something that I noticed right here at the very beginning. We get r squared cosine squared plus r squared sine squared. If I factor out an r squared from that, then we get sine squared plus cosine squared. And I hope maybe you remember the trigonometric property, sine squared plus cosine squared equals 1. Very, very important and very, very helpful property. So sine squared plus cosine squared equals 1. If we can combine those, we'll get 1. So we'll get, let's do that. Let's do that. So if I factor it out, I get r squared, let's see, cosine squared theta plus sine squared theta. And that, and then plus all this rest, plus all the rest of this, 6r cosine theta plus 4r sine theta equals 0. Great. Let's see. So that, fortunately, gives us that the cosine squared plus sine squared, that is 1. So now I've got r squared times 1, or just r squared, and then plus 6r cosine theta plus 4r sine theta. All right. So we can continue going here. We want to solve for r as our goal. And so we're going to do everything we can to solve for r. Let's try first by, let's try factoring out that r on the left and right side, because I can, or maybe even better than factoring, I've noticed that there's an r that's among all three of these terms. We've got an r in the r squared. We've got an r in the r squared. We've got an r in the 6r cosine theta and an r in the 4r sine theta. I can divide by r, and I can even divide r on all sides. And if I divide r on all sides, it'll get rid of one of them. So I can say this divided by r, this divided by all this divided by r, this divided by r, and this last term divided by r. If it's confusing by the fact that I just took every single term and divided by r, you can kind of think of it as I took the entire thing and divided it by r, and then I split it up into multiple fractions. Let me see if that might be confusing. Here's a quick aside if that doesn't make sense. So I get r squared plus 6r cosine theta plus 4r sine theta equals 0. I divide the left side by r, divide the right side by r, and I can split that up now. I can split the left side up to r squared over r plus 6r cosine theta divided by r plus 4r sine theta divided by r equals 0 divided by r. That's all I did. And I just kind of skipped that step by dividing both sides, by dividing every term by r. That's essentially what I did. Anyway, all that to say, the r squared and r cancels out to just be r. These r's cancel out, and these r's cancel out, which is very convenient for us. That leaves us with, plus 6 cosine theta plus 4 sine theta equals 0. Oh, now we're almost done. We just get r by itself, and we can do that pretty simply at this point. We will say, if we subtract the cosine and sine from both sides, we'll get r equals negative 6 cosine theta plus 4 sine theta. Now, before I go too far, let me just backtrack for a second and go back to that 0 divided by r. If you were confused by this and you felt like this is problematic, there is an intuition probably in your head as to why. A while ago, I said when you divide by x, we create problems. We've created problems to divide by x because x is a variable, and x being a variable can do really strange things if you divide by x. You can actually lose important information because it's such a variable. It can change so much. However, with r, at least in this case, I don't want you to worry about that. You don't need to worry about that, because I think maybe a way of thinking about it is that this r isn't quite like a variable. Maybe you can think of it more of just like a number we don't know yet. Maybe that's be more helpful. Or in other words, this is fine unless we divide by 0. If we divide by 0, if r is 0, then we've got problems because we've got 0 divided by 0. Or if any of this, r equals 0, we'd have problems. So r shouldn't be 0, usually. But think about this. So normally we would say with this, we would say that r equals negative 6 cosine theta and 4 sine theta, and r is not equal to 0. And again, we'd say that because we divided both sides by r. We can't divide both sides by r if r equals 0. So we're going to go ahead and make sure we're going to specify and say r does not equal 0, because if r does equal 0, then we'd have problems. So we'd say up here, r does not equal 0. But here's the catch. If you look back at our initial equation, you see x plus 3 squared plus y plus 2 squared equals 13. Can you think about what kind of equation that is? If you think very carefully, you might realize that's a circle. This actually is a circle. Just been translated a bit, because x squared plus y squared equals r squared right down here. That's the equation of a circle. So if that being the case, then we could say that if this is a circle, then the radius is probably not going to be 0, especially with the equation that we're working with. The radius will never be 0. If it was 0, then it'd just be a point, and we're not dealing with point. We're dealing with a full-blown circle. In other words, this whole r equals 0 thing is not that important. Okay, I hope I didn't confuse you with all that. The point is, normally if you had troubles there, I hope that cleared it up. If not, don't really worry about it. It's fine. Okay. So x plus 3 squared plus y plus 2 squared equals 13. We did the first part. The first part was this equation. This is the answer to the first part of the problem. And then the next part is to sketch a graph of the rectangular equation, and don't use a grapher. All right, we can do that. So this would be section 2. So section 2 says we have x plus 3 squared and y plus 2 squared equals 13. So x plus 3 squared plus y plus 2 squared equals 13. And we want to sketch that by hand. So remember what the way the formula works. The base formula for a circle, as you might recognize, this is a circle, is x squared plus y squared equals a radius squared. Okay, so let's see. Normally, let's look at 13 first, because that might be the simplest thing to think about. At 13 is the radius squared. So the radius squared equals 13. That's the radius. That's how big the circle is. And that means that it's not the moon. If the radius squared is 13, we'll want to take the square root of both sides to figure out what the radius is. So I'll square both sides, and the radius equals the square root of 13, which is about, that's the square root of a prime number, but that is about 3.6. You could say about 3.606. Okay, so that's the radius. We can start with that. That accounts for the first part of it. How about that x plus 3 and the y plus 2? We need to figure out a way to account for that as well. So we've accounted for this 13, but we need to account for the x plus 3 and the y plus 2. We need to figure out what to do with those. Okay, so normally it's x squared and y squared, but that plus 3 and that plus 2 shows it's not just a normal, it's not just x, or it's not just y. You might recognize this as a transformation. So how do we transform this? Well, I want you to make sure that you're remembering that this is not the normal way. Well, there's a couple ways to transform things, and don't want you to be confused. You might say this goes up to the right 3 and up 2. But remember, this is more of like these are both, if you had an equation like this, you'd equation like y equals x minus 2 squared. You remember that that x follows the opposite rule that we're used to. This would mean we go to the right 2. If we had x minus 2 squared. So and you kind of think they're both in parentheses like this, and since they're both in parentheses, they both kind of follow that rule, kind of do the opposite of what you anticipate. In the sense that we had to put in, if this was x minus 2 squared, we'd graph this as we go to the 1, 2, and at x equals 2, it'll act like it's at 0. At x equals 2, it'll act like it's 0. It's at 0, so it'll go something like this. Similarly, in order for the circle to act like it's at 0, in order for us to act like we're at the center, we need to put in -3 for x and negative 2 for y, which means that our graph, our center of our graph, the center of our graph is going to start at negative 3, negative 2. In other words, because they're both in parentheses, I really want to make this clear. Because they're both in parentheses, we are going to the left by 3, and we're going down by 2. So our center is negative 3, negative 2, this point right here. Okay, and then we're making a radius of about 3.6. So let's see. I'll start at the top. That's about right up here. The bottom is right about down here. And let's see, the sides right about there and there. No, not there. That's right about 3.6 to the left. It's right about here. Okay, so that's about our circle. Something about those lines. So we're gonna go ahead and draw that, and that should be our answer. The radius is never 0. It's a constant number. It's 3.6, and it's all the way around. It's a pretty lopsided circle, but that would be the graph of the answer. Okay, that was step 2. Step 3 says support your hand sketch by graphing the polar equation with your grapher. Okay, let's actually graph that polar equation and see what it looks like. So we go to mode, make sure we're in polar, go to y equals for polar, and then we're going to just plug in the numbers. So our polar equation that we made is r equals negative 6 cosine theta plus 4 sine theta. There it is. And that gets us, if we're not zoomed out, to 100. Oh, it looks like I am in the wrong mode. I am still in degree mode. I want to be in radian mode because all this is in terms of radians. The radius, radians, you want to be in radian mode. Otherwise you get something really weird. There it is. And it looks like my graph is a little bit off. I wonder why that is. Did I write this a little bit wrong? Minus, I wrote a, oops, let's fix that right now. This is a plus 4 sine theta. This should be a minus 4 sine theta, excuse me. Because we subtracted 4 sine theta from both sides. This should be a minus 4 sine theta. There we go. There we go. That's more like what we're looking for. And that looks just like the graph that we made. There it is. So that's the answer. Good, that's it. Oh man, I hope I didn't confuse you too much here. All right. If you have more questions, please let me know. I'm here to help however I can. All right, next problem. We're going to complete the following for r equals negative 8 sine theta. So it gives us a function of sorts. It gives us a relation in terms of r, in terms of the polar coordinates. It wouldn't be a function because a function would be something that where it passes the vertical line test. But this probably doesn't pass that vertical line test, as you can probably imagine. Okay, anyway, make a table of values with theta equals pi over 4, pi over 2, 5 pi over 6, pi, 4 pi over 3, and 2 pi. That's the first step. And then secondly, just plot the points from the table and graph the curve for 0 to 2 pi for theta. Okay, that's what we're going to do. We'll start with the table. So theta is going to go at top. Theta is going to be like our x, and our y is going to be like the radius. So we'll start with pi over 4. Let's see, negative 8 sine of theta. So pi over 4, the sine of pi over, let's just go ahead and figure this out. The sine of pi over 4 is square root of the sine of pi over 4 equals the square root of 2 over 2. If we did the sine of pi over 2, that is 90 degrees, and that is the value of 1. Sine of 5 pi over 6, that would be, let's see, that's 150 degrees, that's 1/2, yes, that's 1/2. And sine of pi, that's obviously 180 degrees, and that would be 0. And then 4/3 pi, sine of 4/3 pi, that would be, yeah, that's 240. And 240 would be negative root 3 over 2. And finally, 2 pi, sine of 2 pi would be just 0 again. The y value is 0. These are all the y values of the coordinates on the unit circle again. So this is negative 8 times the sine of theta. So we'll just graph those. We'll just put in those. So negative 8 times the square root of 2 over 2, that'd be negative 4 root 2. Negative 4 root 2, square root 2. And then we've got, if we have pi over 2, let's see, pi over 2, the square root of, well, negative 8 times 1 would be negative 8. And then for 5 pi over 6, we have, what do we have? 5 pi over 6, we have 1/2. Negative 8 times 1/2 is negative 4. For pi, we have 0, so that's 0. Negative 8 times that times 0 is 0. 4 pi over 3, that gives you negative root 3 over 2, which is negative 4. No, that's positive 4 root 3. Yeah, positive 4 root 3. Okay, and or square root 3, and then we have 2 pi. 2 pi is 0, so we still have 0. Okay, so now we plot the points from the table, and we'll graph the curve for 0 to 2 pi. Let's do that. Okay, so if let's quickly change colors for this one. So that was A. We did A. Now we go to B. Excuse me. Let's go ahead and make our graph here. Graph. I'm not going to make these. I mean, you can make them as exact as you like. I mean, it's good to be more precise, but I'm just going to make them pretty close. I'm making them pretty general. I'm not going to make it 100% for the sake of your own time. Let's see. Pi over 4. Well, actually, I can make them. I can make them exact. That sounds like a good practice. Let's go ahead and do that. So pi over 4. That means if we're going pi over 4 degrees, that's 45 degrees. We're going to go negative 4 root 2. So our size is going to be negative 4 root 2. And if I make an angle, it's negative 4 times the root 2. How big are these sides? The sides and the sides. How big will each side be if each side is equal? Because we're in a 45-degree angle. And we can say, okay, that is going to be 4 root 2. I mean, you can kind of imagine if you want to. I'm going to pull out the calculator and just make it an approximation. So I think I don't want to waste your time. So 4 times the square root of 2 is 5.4656. So that's about a distance of 5. So that's about 1, 2, 3, 4, 5. Yeah, about that. So we get something like that. Or let's go ahead and write that as negative. Oh, it's negative 4 root 2. Excuse me. This is negative 4 root 2, so we'll go backwards 4 root 2. So we'll do negative 4 root 2. Okay. So that's 1 point. And let's see. If we did pi over 2, it's straight up, we get negative 8. We get negative 8. That's pretty simple. 1, 2, 3, 4, 5. So we go 90. Pi over 2 is 90 degrees. 90 degrees. Except instead of going forward, because it's negative 8, we'll go backwards. We'll go backwards 8. So go 1, 2, 3, 4, 5, 6, 7, 8. Okay. So that's 8 there. And let's see. We will have, the next one will be 5 pi over 6 will be negative 4. So 5 pi over 6 is negative 4. So that gives us, let's see, that's about 5 pi over 6 negative 4. That's right about over here, I'd imagine. Yeah, that makes rough sense. Or maybe it'd be 5 pi over 6 is this angle over here. It's this angle over here. So that means we'd go back and be right about here, I believe. That's about 4-ish. And oh man, this is gonna be an awful sketch. I want to make this a little more accurate so it's not awful. Okay, this is going to be about, I guess relative to everything else, about this distance here. And let's see, pi would be 0. And so that's simple. No matter if we get all the way pi, it's going to be right in 0. And 4 pi over 3, 4 pi over 3 be 4/3 pi. Okay, so 4 pi over 3, let's see, that's 240 degrees. Yeah, that's 240 degrees. So we're going to go ahead and go 240. It's about down here. That's the same spot. So 4 wants to go 4/3 pi. So that's the same spot as before. So plot that. And then 2 pi is 0 again. So if I was to sketch all this together, so it kind of looks like, well, maybe the best way to put it is something kind of like, is this fair? This seems fair. We've got 4 points. So here's what I'm thinking. We've got 4 points, and we started at pi over 4 down. We started at pi over 4 down here, and then we moved over to the bottom, and then we moved to the right, and then we moved to the top, and then moved left, and then we moved left again, and then after that, after we skipped the whole lot and went from 4/3 pi all the way to 2 pi, we went all the way to the top again. So I'm thinking this is making a clockwise circle. That's what it seems to be doing. As we go around pi, it seems to be making this clockwise circle. And that is exactly what it's doing. Looks like it is making this clockwise circle. So that'll be our answer for that one. Great. Okay, the location given in polar coordinates of two. Oh, it looks like we're finished here. So I gotta. It's time for a break. Welcome to what I hope will be the last of our 3 sessions, or last of our sessions here. This probably my 4 sessions now. Let's go ahead and finish up these last 3 problems. That's what we're trying to do. Okay. The location given in polar coordinates of 2 planes is 5 miles and 15 degrees and 2 miles and 79 degrees. And it asks us to find the difference between the 2 airplanes. Okay. Let's first draw a little image here so you can kind of get a framework of what's happening. I'm going to draw these 2 axes. The lines are getting straighter, that's nice. And let's see, our first line can be green. So we'll say 15 degrees down here, 15 degrees, and that's about 5 miles. And let's see, we've got another axis. Let's say, I don't know, let's say it's red. And we'll say this is 79 degrees, but it's not 5 miles, it's only about 2 miles. So we'll say 79 degrees and 2 miles. And 2 miles. Okay, and it asks us to find the difference between the 2. Find the difference between these two lines, or between these 2 airplanes. So that's the distance. This blue is the distance between the 2 airplanes. So we need to find the distance. So if we wanted to find, so basically we're trying to find the distance between this point, this first point here, and this point right here. And, you know, how do we do that? If you wanted to find the distance between 2 points, normally we'd use something like the distance formula. And that'd work great to just use the distance formula to find the distance between 2 points, and that would work. Except now we have polar coordinates. We have the coordinate, let's see, 279, and the coordinate, let's see, that's 515. So those are not rectangular coordinates. But here's what we can do. If we convert these polar coordinates to rectangular coordinates, then we can make it work. We can use the distance formula. All right. Let's see. Just as a reminder of what the distance formula is, it comes straight out of the Pythagorean theorem. It is the distance equals the square roots of y2 minus y1 squared plus x2 minus x1 squared. So the x distance squared plus the y distance squared equals the distance squared. Okay, so let's go ahead and convert from rectangular to polar. So sorry, from polar to rectangular. Let's remember our little equations to convert. We've got x equals r cosine theta. we've got y equals r sine theta, and we've got a few other equations. We don't even need to use those. We can just work with just these, and that works just fine and dandy. Okay, so for the first point, we'd say that x equals 2 times the cosine of 79 degrees. Then we'd say y equals 2 times the sine of 79 degrees. Okay. And let's call the red one. Let's call the red one 0.1, just for the sake of the distance formula when it comes up later. And the green one 0.2. I just want to make that kind of helpful. Okay. And then as far as the green one goes, the green will be x equals 5 times the cosine of 15 degrees. And y will be 5 times the sine of 15 degrees. Okay, let's go ahead and pull out our calculator and just compute these values. Okay, so we'll make sure we are in degree mode. So I want to be in, not fraction mode, we want to be in degree mode. And then we'll just plug in these numbers. Let's see, I am in alpha, I don't want to be in alpha. Okay, let's say we have 2 times the cosine of 79, and that is 0.381. So x equals 0.381. Interesting. All right, 0.381. And then 2 times the sine of 79, that would be 1.963. Great. Okay, and then for the green one, we have 5 times the cosine of 15, and which is 4.829. So x equals 4.82. Actually, that's 830. And y equals 5 times the sine of 15 degrees, which gives us 1.924. 1.924. Great. Now let's go ahead and use the distance formula to solve for this. So this is the red one is our first point, so we'll make that x1 and that'll be x1 and y1. And then the second point is our green point, so we'll make that x2 and y2. Let's go ahead and plug those in. So we've got the square root of, so for our distance formula, distance equals the square root of 1.924 minus 1.963 squared. And we will say that is, we're going to add to that, let's see, 4.830 minus 0.381 squared. And we'll take the square root of all that. Okay, let's just plug it in and see what we get. So let's see. We've got the square root of let's make our open parentheses, 1.924 minus 1.963, and we'll square that, and we will add to that the 4.830 minus 0.381, and that's squared, and that gives us 4.449. So the distance, principally, is 4.449. D equals 4.449. We have to round up. That is, yeah, that's it. And so that's our answer. That is the answer. Or if you want to put it in a unit as well, you can say 4.449 miles. And that's our answer. That is the number of miles in difference. Great. A square, let's actually get this up. A square with sides of length A and center at the origin has 2 sides parallel to the x-axis. Find the polar coordinates of the vertices. This one's a very strange problem because it involves a lot of words, and so if English is not your native language, I can see how this one would be especially difficult. Let's break down what it's saying, step by step. Okay, it says a square. We've got a square with sides of length A. So if it's a square, it means all 90 degrees. Get 90 degrees all over. and each of these are the same size. Each side is the same size, and each side is size A. So this is A, this is A, this is A, this is A. So sides length A, and a center at the origin. So the center is at the origin. That means that let's see, if we were to plot this on an axis, let's say, plot this on an axis. Okay. That means that it centers at the origin. So I'll just make some arbitrary size square. Okay. Okay. And great. Okay, so that's our square. Again, it's got 4 right angles. Each side is size A, size A, size A, size A, and center is at the origin. Let's see, it has 2 sides. Has 2 sides parallel to the x-axis. Okay, so it's just saying the 2 of its sides are parallel to the x-axis. Let's see. Oh, this has got 2 sides parallel to the x-axis. This side's parallel. That side's parallel. Just like that. Those are all both parallel to the x-axis. Here's an example of something that wouldn't be parallel to the x-axis. If we had a square and it looked kind of like a diamond, something like that, that kind of square would not be parallel to. There would be no sides parallel to the x-axis. Or if it was just kind of crooked, if we had a square that was kind of like this, that's a really terrible square. It's not really that accurately drawn. But if it was askew at all, it wouldn't work. But that means if it's parallel to the x-axis, that means that those 2 lines are parallel, that means there's right angles everywhere. There's a right angle here and here and here and here, and all these are right angles. There's right angles here. There's right angles here. There's right angles everywhere because they're parallel. And that parallel creates some perpendicular lines. That means if there's right angles on parallel lines, there's a line going through them. It just creates a lot of perpendicular lines. That's all we're dealing with. Lines at right angles of each other. Okay. So, okay, here we go. Now we need to find the polar coordinates of the vertices. Okay, find the polar coordinates of the vertices. These are the 4 vertices right here. This is a vertex, 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 vertex. And we need to find the polar coordinates of those vertices. Let's go ahead and work this way. So we need to find this polar coordinate, that polar coordinate. And you'll realize right off the bat, you're not going to find some exact numbers. There's no exact number that'll work with this. It's going to be something in terms of A, is what those vertices are. And so you'll find you're trying to figure out, in essence, what you're trying to do is you're going to try to figure out this distance, the distance from the center to a vertex. But if you can find the distance from the center to the vertex, and then you can find, then you'll know it, because these are all going to be. If these are all 90 degrees, if there's 90 degree angles everywhere, then all these will be 45 degrees. And this will be 45 degrees from 90. And this will be 45 degrees from that. And so on. So all the values get a bunch of different chunks of 45 degrees. So you're kind of thinking 45 degrees is one way to think about it. And then find the distance. Realizing that that one whole side is A. And so half of a side, this is like, if you were to say just this section over here, just this is A over 2. So you want to kind of think about those things. Those will be really helpful tools. And in fact, I think you can figure it out from there on your own. I imagine, I believe in you. I bet you can figure this out on your own from here with information that I've given you. If you still want more help on this, just ask me. Welcome. I'm happy to give you more information. But I think you can figure this out on your own from here, on how to figure out what those polar coordinates are. So I will leave you there with that. Okay, good. Move on to the next problem. So, I mean, I finished on your. Actually, I write it in the bottom. All right, finish on your own. Okay. So graph the point on a polar grid. That's going to be pretty straightforward here. This, unfortunately, they leave us on a really straightforward finish. So we're going to graph this point on a polar grid. Let's see, we're going to have pi over 2, which is, let's see, that's pi over 2 is 90 degrees. So 90 degrees. So we're going the direction of pi over 2, and we're going to go negative 3 from pi over 2. So we go backwards 3. We'll go backwards negative 1, negative 2, negative 3. And that will be our point. This right here is our point. We went pi over 2 up. This is pi over 2. And then we went, instead of going forwards, we went backwards. We went back in negative 3, because this is our angle, and this is our radius. And that's it. Cool. And I think that's everything left. So good luck. If you haven't, I hope this was helpful. I hope this was moderately, in some ways, perhaps enjoyable. At least didn't, at the very least, I hope it didn't cause too much suffering. If you have any more questions, please let me know. I'm here to help however I can. And I'm looking forward to seeing your good work. Thanks.